A useful way to understand quantifiers is to think of them as big versions of and or. So let's see this through an example. So let's consider two predicates. Let's do odd of x to mean that x is odd. And let's do the less than 5 of x to mean that x is less than 5. And let's look at this. So let's consider the statement for every x odd of x. So this will actually be equivalent to a big and over the whole domain. So if the domain is -3, if the domain is -3 and 3, this will just be the following. This will be odd of -3 and odd of 3. Why? Because if it's true that for every x, odd of x has to be true, that's the same as just doing a huge and over your whole domain. So it needs to be true that odd of x is true for everyone in the domain. So in this case, the domain has two elements, -3 and 3, and so these need to be true. So this will be equivalent. So odd of -3 is true, and odd of 3 is true, and true is true, if we go back to the truth table for that. And so it is true that for every x, odd of x holds for this domain, right? Now, if we look at there exist, for example, so there exists x such that odd of x, then instead of an and, this is going to be like a large or, because you only need to have this be true for one of the elements. So we go again over the whole domain and we check odd of -3 or odd of 3. And so again, this will just be true or true, which is true. And so, of course, odd of x will be, there exists an x such that odd of x is true because in this case, at least one of them is true, and that will follow from the or. Now, if we take, for example, the less than, so is it true that for every x less than 5 of x is true? Well, once again, you just need to check it for each one. Less than 5 of x. You need to check for each one, so less than 5 of -3. And less than 5 of 3. And so, of course, -3 is less than 5, so this is true. And less than 5 of 3 is also true, because 3 is less than 5. So this is true, and so this ends up being true. And here, let's say, for example, to get more of a false example also, let's say that here I add the number 6. So now I need to come down here and erase this part. So let's erase this. And so now I would need to check, so odd of x, I need to check for -3, for 3, and odd of 6. Now in this case, we will have, so odd of -3 was true, and odd of 3 was true, but now odd of 6 is false. And we know that when you do an and with false, with at least one false, you will get a false. So now it is not true that for this domain with 6 that every x is odd, right? Is it true that there exists? Well, of course, in this case, we'll have to add an or here, odd of 6. And so now we will have true or false. But the way or works, you just need to have at least one of them to be true. So this will just be true itself, right? And you can do the same in the bottom if you go for and less than 5 of 6. This will be false. So this will be true and false, which will be false. Okay. Now, okay, that works quite well for finite domains. For infinite domains, it will actually work the same. It maybe, if you're not too accustomed with dealing with infinite stuff, it might seem a little bit unnatural, but we'll write it anyways here. So imagine it's over the integers, so we're doing it for every integer. Then what happens is, and let's just look at odd. So for every x, odd of x is true, this would be equivalent to sort of doing an infinite, like an infinite amount of ands with every single integer. So you'd have odd of -1 and odd of 0 and odd of 1 and so on. So you'd have odd of everything appearing. Now, of course, you have like an infinite but we saw that for an and, if any single one of them is false, then this will be false itself. So in this case, odd of odd of 0 will be false because 0 is an even number. And so you have an infinite ands, but there's at least one false. This means that this will be false, right? Now, when you do there exists odd of x, so there exists an x such that that number is odd, again, over the integers, you'll have an infinite amount of ors. So you'll have your odd of -1, or odd of 0, or odd of 1. And now it's the case that there exists at least one of them that is true. And we saw that when you do any amount of ands, and in this case even an infinite amount of any amount of ors, and in this case even an infinite amount of ors, if at least one of them is true, then the whole thing will be true. And so this is a nice way of thinking about the quantifiers, right? So you can think of them, so you can think of a for every as a big version of and, it's a bunch of ands. And you can think of the there exists as a big version of ors. And so it's like a bunch of ors.